40,000 feet above your head, there's a river of air moving faster than any hurricane on the ground ever could. And this year, it's been behaving in ways meteorologists don't see very often. When people say the jet stream just broke, they're not exaggerating for effect. They're describing a genuine shift in the exact mechanism that decides whether the UK gets storms, sunshine, floods, or heat waves, and the same mechanism has been driving some of the wildest weather headlines out of the United States too. To understand what actually broke, you first need to understand what the jet stream normally does. Picture a fast-moving current of air roughly 6 to 9 miles above the ground, flowing west to east across the planet, driven by the temperature difference between cold polar air and warmer air further south. Under normal, healthy conditions, that current stays relatively straight and stable, acting like a boundary line that keeps cold Arctic air locked up in the north and warmer air further south, while steering storm systems along a fairly predictable path across the Atlantic and into Europe. When meteorologists talk about the jet stream breaking, they usually mean one of two things going wrong with that boundary. Either it becomes unusually meandering, developing large, slow-moving loops that dip much further south, or swing much further north than normal, or it splits entirely into two separate branches, a phenomenon called split flow, where one stream curves north and another dives south with nothing steering weather systems predictably along a single path anymore. Both versions share the same underlying consequence. Instead of weather moving through in a normal, orderly sequence, it gets stuck, amplified, or sent somewhere it wouldn't normally go. This year, the UK experienced both versions back-to-back within the same 12 months, which is part of why this particular story has drawn so much attention. Back in January 2026, meteorologists tracking a run of named storms, including Storm Chandra, Storm Goretti, and Storm Ingrid, pointed directly to an unusually powerful, southerly shifted jet stream that dragged one Atlantic low-pressure system after another into the UK with barely any recovery time between them. According to Met Office analysis at the time, that southerly shift traced back to a stark temperature contrast between a deep Arctic cold spell gripping North America, cold severe enough that hundreds of thousands of homes lost power and dozens of people died, and much milder air sitting further south. A contrast that acts like fuel, energizing and strengthening the jet stream well beyond its usual winter intensity. The result was a January that left Northern Ireland with its wettest January in 149 years, Cornwall with its wettest January on record, and southern England with its sixth wettest January since records began in 1836. Storm Chandra specifically brought an unusual easterly wind direction to parts of Northern Ireland, a wind direction that almost never produces severe weather in the UK, precisely because the jet stream had shifted the entire storm track into an atypical position. Then, within a matter of months, the picture flipped almost completely. By late spring and through the summer, a very different kind of jet stream disruption took hold. One meteorologist described using an entirely different vocabulary: blocking. A blocking pattern happens when a large, stubborn area of high pressure effectively parks itself in place and refuses to move, physically obstructing the jet stream's normal path and forcing it to divert dramatically around the block, sometimes for weeks at a time. Meteorologists specifically identified an omega block, a kink in the jet stream shaped like the Greek letter omega that stalls weather systems in place. This year, that block repeatedly set up either directly over the UK or just to its north, dragging superheated air north off the Sahara, sometimes nicknamed the Spanish plume, in a pattern that pushed temperatures 14 to 18 degrees Celsius above normal for late June across a swath of Europe from Portugal to Poland. The consequences were almost the exact opposite of January's relentless storm parade. Instead of a fast-moving jet stream dragging system after system across the Atlantic, a displaced jet stream let high pressure dominate for extended stretches, bringing the kind of prolonged, stagnant heat that produced this year's remarkable run of records. The numbers here are genuinely without precedent in the UK weather record. The UK's May heatwave broke the country's all-time record for that month twice within 24 hours, first when 34. 8 degrees Celsius was recorded at Kew Gardens in London on the 25th, then again the following day when 35.1 degrees was recorded at the same location, smashing a record that had stood since 1922. By July, 2026 had become the first year in the UK weather record to see temperatures of 35 degrees Celsius or higher in May, June, and July, all within the same calendar year. The Met Office also confirmed a record 8 days with temperatures exceeding 34 degrees across the year, surpassing the previous benchmark jointly held by 1976 and 2020, with the UK logging more days above 30 degrees by mid-July than the entire summer of 1976, the year that has served as British shorthand for extreme heat for half a century. A peer-reviewed analysis involving the Met Office, the London School of Hygiene and Tropical Medicine, and Imperial College London found that climate change specifically drove an estimated 42% of the roughly 2,700 heat-related deaths recorded in England and Wales across the May and June heat events alone. Both of these outcomes, the relentless winter storm parade and the record-breaking summer heat blocking pattern, trace back to the same underlying cause, even though they produced almost opposite weather. A wavier, more erratic jet stream, whether it's meandering south to drag in repeated Atlantic storms or getting physically blocked in place by a stubborn area of high pressure, is now widely understood by climate scientists as one of the clearer fingerprints of a warming world. Here's the mechanism researchers point to most often. The jet stream is powered by the temperature contrast between the cold Arctic and the warmer air further south, but the Arctic has been warming significantly faster than the rest of the planet, a phenomenon called Arctic amplification. As that temperature gap between the pole and the mid-latitudes narrows, the jet stream loses some of the driving force that normally keeps it fast, tight, and relatively straight. A weaker jet stream tends to become wavier and more prone to getting stuck in place, whether that means stuck delivering storm after storm along an unusually southern path, or stuck allowing a heat-trapping ridge of high pressure to sit motionless for weeks. That distinction, a weakened driving force rather than a stronger one, runs counter to what a lot of people assume when they picture extreme weather being linked to a more powerful atmosphere. In this case, it's closer to the opposite. A jet stream with less energy pushing it along tends to wander more and get trapped more easily, producing longer, more persistent spells of whatever weather happens to be sitting underneath it at the time. There's an additional layer of complexity worth understanding too, one that goes beyond Arctic amplification alone. Ocean temperature patterns thousands of miles away can also nudge the jet stream into unusual configurations. Sea surface temperatures in the tropical Pacific have been watched closely for exactly this reason throughout this year's transition between ocean cycle phases, since a warmer tropical Pacific tends to encourage what meteorologists call split flow, where the jet stream effectively divides into two separate branches, a stronger, more southerly subtropical branch, and a northern polar branch pushed further toward the Arctic than usual. That kind of split doesn't just affect one country in isolation. It reshapes storm tracks and temperature patterns across an entire hemisphere simultaneously, which is part of why so many different regions have reported unusually erratic jet stream behavior within the same 12-month stretch. Climate researchers studying this year's clustering of extremes have made a point worth sitting with directly. The average summer temperature creeping up over time matters less, for practical purposes, than the increasing frequency and intensity of extreme events themselves, extremes that compound and stack on top of each other in ways that infrastructure, ecosystems, and financial models built for a cooler, more stable climate were never designed to handle. 3 separate heat waves distinct enough to break records in 3 different months isn't just an unlucky coincidence sitting on top of a normal year. It's closer to what a wavier, more erratic jet stream tends to produce once it settles into a blocking pattern and refuses to budge. This connects directly to something researchers documented in dramatic fashion across the Atlantic in March, in an event scientists have since studied as one of the more striking examples of what they call hydroclimate whiplash. In mid-March 2026, a jet stream disruption produced an almost unbelievable spread of simultaneous extremes across the United States. An extreme, Category 5 rated blizzard, unofficially named Winter Storm Iona, dumped as much as 4 feet of snow around the Great Lakes and upper Midwest, with the storm's central pressure dropping to levels typically associated with strong hurricanes. In the days surrounding it, 3 separate severe weather outbreaks produced a combined 177 tornadoes across the central and eastern United States, including one supercell that produced what appeared to be an Illinois state record hailstone over 6.5 inches in diameter. At the same time, an unprecedented early-season heat dome built across the Southwest, with forecasters warning of 5 straight days of triple-digit heat in Phoenix, a level of March heat the region essentially never sees. And in Hawaii, a slow-moving subtropical system known as a Kona low tapped into deep tropical moisture, dumping more than 2 feet of rain, triggering statewide flood watches, and bringing wind gusts over 100 miles an hour to the volcanic summits of the Big Island. Meteorologists at the time described the underlying pattern bluntly as a jet stream gone wild, colliding with the normal seasonal transition between cold and warm air in a way that pushed nearly every category of extreme weather to its limits simultaneously within a single week. So what does a broken jet stream actually mean going forward, beyond explaining why this particular year has felt so relentless on both sides of the Atlantic? It means the traditional assumption that extreme weather arrives, then eases, then gives way to a return toward average conditions is becoming less reliable than it used to be. A wavier, more easily blocked jet stream doesn't just produce occasional extreme days, it produces extreme spells, storms that queue up one after another without normal breathing room, or heat waves that refuse to break for weeks at a time, because the very system that used to reliably move weather along has lost some of the energy that once kept it doing so. For a country like the UK, built around infrastructure, agriculture, and public health systems, calibrated to a narrower, more predictable range of weather, That shift matters enormously. Reservoirs designed around historical rainfall patterns, railways engineered for a specific temperature corridor, and flood defenses built using decades-old rainfall records are now regularly facing records broken within a single afternoon rather than standing for another 60 years, as this year has repeatedly demonstrated on both sides of the Atlantic. It's worth understanding how forecasters actually track something as invisible as a river of air several miles above the ground, because it isn't guesswork. Weather balloons launch twice daily from stations around the world. Satellite measurements of temperature and pressure at different altitudes, and aircraft-mounted sensors all feed continuous data into the same supercomputer models used to predict storms and heat waves days in advance. Meteorologists specifically watch the jet stream's position, its speed, and how wavy or straight its path looks on any given day. Because a jet stream running fast and relatively flat tends to mean quick-moving, changeable weather passing through efficiently, while a slow, deeply looping jet stream is the clearest early warning sign that whatever pattern currently sits beneath it, stormy or scorching, is likely to stick around far longer than anyone would prefer. That's also why the long-range seasonal forecasts remain so notoriously difficult, even for the world's most sophisticated models. Predicting exactly when and where the jet stream will buckle into a loop, split into two branches, or get physically blocked by a stubborn area of high pressure involves so many interacting variables. Arctic temperatures, ocean patterns thousands of miles away, soil moisture, even conditions in the stratosphere above the jet stream itself. That forecaster confidence tends to stay low until the pattern is only a week or two away from actually happening. That's precisely the uncertainty that left forecasters genuinely divided months in advance over exactly how this year's pattern would play out, before it ultimately delivered both extremes, storm-battered and heat-broken, within the same 12 months.